Okay, so in this video I want to do a few examples of the antiderivative. So one quick example is from physics. Suppose that the acceleration at time t is due only to the gravity, And so, do we remember the gravitational constant? Um, it's approximately 9.8 meters per second squared on the surface of the Earth, and that is just an approximation. And so if we assume that the only thing affecting an object in free fall is the force of gravity, then we can just write that a of t is constant, right? The acceleration would be our constant. You know what? To make the down be negative, we could write minus 9.8. Okay, and so what would the velocity function be then? To find the velocity, we would need to anti-differentiate, and so we would have minus 9.8. I'm going to use t instead of x now. So that would be times t, 9.8 times t, plus a constant, right? And so what does this constant represent? Notice that the constant is the velocity at time 0, and so we typically would call this constant the initial velocity. So that's the velocity at time 0. And so actually that is how you would find the C1. We would have to be given an initial position or initial velocity, right? And so with that we can find our displacement function, right? That's going to be minus 9.8. I guess you could just write g instead of 9.8. Well, let's go ahead and keep 9.8 over 2 d squared plus c1 times t plus c2. Is there a physical interpretation of c2? Well, notice again that if you plug in t equals 0, that would be the initial position, and so c2 is the initial position. And so s of 0 is equal to c2. And so if you anti-differentiate twice, notice that you get an arbitrary constant every time you do that. And so in this case we ended up with two arbitrary constants, but they do have some kind of physical interpretation, right? We could find c1 and c2 if I give you extra information about the function. Good. All right. And so actually you can kind of see here why we use a parabolic function for the displacement of an object if the acceleration is only due to gravity. Good. All right, let's do something a little bit more concrete here without a lot of arrows. Suppose that f prime of x, we'll just do the first derivative, e to the x plus 20 times 1 plus x squared to the minus 1 power, and I know that f of 0 equals minus 2. I want to find f of x. How am I going to do that? Well, first we would want to anti-differentiate so that f of x is going to be e to the x plus, now this is 20 over 1 plus x squared, or I should say 20 times 1 over 1 plus x squared. And do you remember seeing this expression before? That's the derivative of the inverse tangent function. So this is going to be e to the x plus 20 times the inverse tangent of x plus c. And now, how am I going to solve for c? I'm going to use this extra piece of information here so that f of 0 is minus 2. And so when I plug in x equals 0, I want minus 2, so minus 2 is equal to e to the 0 plus 20 times the inverse tangent of 0 plus c. Good. E to the 0 equals 1. And what's the inverse tangent of 0? Well, that's the angle whose tangent is 0. Do you remember if the tangent goes through the origin? It does, and so this is 0. And so plugging those in, you have minus 2 equals 1 plus 0 plus c. And so it looks like c is minus 3. Good. And so the original function then, we know, was e to the x plus 20 times the inverse tangent of x minus 3. Good. And so notice that when you take the general antiderivative, how many functions does this represent? That's an infinite number of functions, right? Infinite number of functions. But when you solve for an initial condition, that solves for c, and so you only get a single solution. Okay, or a single answer, a single function, we can say. Good. All right. How about one more? How about a second derivative? So example, how about if f double prime of x equals 20 x cubed plus 12 x squared plus 4, and I know that f of 0 equals 8, and I know that f prime of 0 equals, or oops, f prime of 1, I guess, equals 5. Oh, that's not f prime, it's just f of 1. So in this case, by the way, you'll notice that I'm giving you two pieces of information because we have the second derivative. And so when we anti-differentiate twice, we're going to have two constants to work with. So let's do the first antiderivative. X to the third power becomes x to the fourth power. And then we divide by 1/4 there, times 20 there in the front, just dropping that down in front. Plus 12 times x squared becomes x cubed, and then take a 1/3, plus 4 times x to the 1 power, right, plus c1. And so just simplifying that before I go further, that's going to be 5x to the 4th plus 4x to the 3rd plus 4x plus c1. Okay, and so now I want to anti-differentiate again. I'm going to go ahead and bring these down. Where am I? F of 0 equals 8, f of 1 equals 5. Good. Now we anti-differentiate again. That's going to be x to the 5th divided by 5, and now I have 5 over 5, right? Plus, that's x to the 4th. Oh, isn't that nice? I love textbook problems. Oh, that one's not going to cancel. Okay, there we go. So there's my antiderivative, and if I simplify that before I go any further, x to the 5th plus x to the 4th plus 2x squared plus c1x plus c2. Good. And now we plug in our two values here and see if we can solve for c1 and c2. And so f of 0 equals 8, so 8 would be 0 plus 0 plus 0 plus 0 plus c2. Oh, that was easy. Okay, how about the other one? F of 1 equals 5, so 5 is equal to 1 plus 2 plus c1, and then c2 is equal to 8, right? So let's just go ahead and plug that in. Good. So what do we get for c1 then? 8, 9, 10, 11, 12. So 5 minus 12, is that minus 7? Good. And so therefore we now have our f of x. X to the 5th plus x to the 4th plus 2x squared plus, that's a minus 7x to the 1 plus 8. There you go. Good. All right. Now, how much time do we have? About a minute. I think I'm going to stop this here, and in the next video we'll be looking at how to graph an antiderivative. So how to find a graphical antiderivative is next. See you there. That'll be fun.